Welcome dear learners. We are continuing quantum chemistry. In this module, we are focusing on the perturbation method. The contents of this module include perturbation theory, the time-independent perturbation theory, non-degenerate perturbation theory, successive correction to unperturbed systems, first order correction to energy, first order correction to wave function. First of all, perturbation theory. We know about two important approximation methods that is commonly used in quantum mechanics. They are the variation principle and the perturbation theory, out of which we covered variation principles in last modules, and the present module focus on perturbation theory. Perturbation theory is an approximation method that describes a complex quantum system in terms of simpler system for which the exact solution is known. This simply means that perturbation theory expresses the solution to a problem in terms of a simple problem which is already solved completely. For example, particle in 1D box with a slanted bottom is a problem where perturbation theory finds its solution in terms of particle in 1D box problem with a regular bottom. This means that particle in 1D box with a regular bottom is a system which is exactly solvable. By using that exactly solvable particle in 1D box problem, we can find out solution to the new problem, that is particle in 1D box with the slanted bottom. Particle in 1D box slanted bottom is a problem where there is no direct solution for Schrodinger wave equation. So, we find out solution to that problem in terms of already solved particle in 1D box problem with the regular bottom. This is what we are doing in perturbation theory. Now, perturbation theory has been categorized into two main types. The first type is known as time-independent perturbation theory, and this time-independent perturbation theory is proposed by Erwin Schrodinger. The second one is time-dependent perturbation theory, and Paul Dirac was the physicist who proposed the time-dependent perturbation theory. In the first part, that is time-independent perturbation theory, we are ignoring the time variable, whereas in the second part, we are considering time as a variable. Moving on to details of the perturbation theory. This theory comprises mathematical methods for finding an approximate solution to a problem by starting from the exact solution of a related simple problem. This point I illustrated by considering the case of particle in 1D box with the slanted bottom, the solution of which are obtained by beginning from particle in 1D box with the regular bottom. And the word perturbation is very significant. The word meaning is small disturbance. Perturbation means small disturbance. In non-degenerate perturbation theory, there is no degeneracy of eigenstates. What do you mean by the term degeneracy? Degeneracy represents more than one arrangement with the same energy. We know about the threefold degenerate nature of the p orbitals. For instance, p orbitals are triply degenerate. That means the arrangement px, py and pz all have same energy. So, the three p orbitals are three different arrangement with the same energy. Hence, p orbitals are said to be triply degenerate. And in non-degenerate perturbation theory, there is no degeneracy of eigenstates. That is, we are the energy states are not degenerate or eigenstates are not degenerate. Now, the first part, the time independent perturbation theory, and we have to proceed mathematically. So, we begin the discussion on time independent perturbation theory by starting from the original Schrodinger wave equation. We have the Schrodinger wave equation, Hamiltonian psi is equal to energy into psi. As we all aware, the term h hat represents minus s cross square by 2m del square plus v, and this is termed as the total energy operator. So, Hamiltonian into psi is equal to energy into psi, and this Hamiltonian is independent of the time variable, and this equation is also independent on time, and hence we use the term time independent perturbation theory. So, the time independent perturbation theory begins from time independent Schrodinger wave equation. This is time independent Schrodinger wave equation. Hamiltonian psi is equal to energy into psi. The Hamiltonian in this expression, in equation 1, can now decomposed into two parts. That is h hat splitted into h hat 0 and lambda h hat dash. The first part, h hat 0, is known as the unperturbed part. The unperturbed part. Once again, the total Hamiltonian of the present system splitted into two parts. This is the total Hamiltonian of the system. It is splitted into two parts. The first part is called unperturbed part, and the second part, that is lambda h hat dash, is known as the perturbation. The second part in equation 2, this second part is known as perturbation. So, I express the complete Hamiltonian of the present system into an unperturbed part, that is h hat 0, and a perturbation, that is lambda h hat dash. It should be noted that lambda is known as the perturbation parameter, and the perturbation parameter measures the deviation of the problem of interest from the unperturbed problem. That is, lambda is a measurement of deviation from original system to the present system. That about lambda. Lambda is called perturbation parameter. This point is very important. The resultant, the entire Hamiltonian has two parts, an unperturbed part and a perturbation. And for convenience, in most of the procedures, we are equating lambda equal to unity for the sake of convenience. It need not be unity, but for convenience, we are taking it as unity. Now, it is further assumed that lambda h hat dash, that is the perturbation part or the perturbation, is very, very less compared to unperturbed part. That is, lambda h hat dash less than h hat 0 or very less than h hat 0. Associated with the unperturbed part, that is h hat 0, there are a set of eigenvalues, and the eigenvalues corresponds to unperturbed part are denoted as E10, E20, En0, etc. We know that energy is the eigenvalue in the Schrodinger wave equation, and here E10, E20, E30, etc. up to En0 are different possible eigenvalues corresponds to unperturbed Hamiltonian, that is h hat 0. The corresponding eigenfunctions are psi10, psi20, psi30, etc. up to psi n0. Thus, in general, we can represent like this: h hat psi n0 is equal to En0 psi n0. Now, it is further assumed that the eigenfunctions psi n and the energy eigenvalues En of the total Hamiltonian S hat can be expressed as a power series of lambda, the perturbation parameter. And this is the power series represents psi n and En. Psi n and En are the wave functions of the present system under consideration. Psi n is mathematically equal to psi n 0 plus lambda psi n 1 plus lambda square psi n 2 lambda 3 psi n 3 etc. lambda raised to n psi n raised to n. Also, energy can be represented as a power series in lambda, and En is equal to En 0 plus lambda En 1 plus lambda square En 2 plus lambda cube En 3 etc. And that about the power series representation of psi n and En associated with the system under consideration. It should be noted that in the expression for psi n, that is equation 5, there is a 0th order term and second order term, first order correction, second order correction, third order correction, etc. Such terms are called, second, third terms are simply known as second order, first order corrections, etc. And in this expression, this we are taking, generally we are considering up to first order correction. Second order correction and higher order correction can also be performed, and that may lead to complex mathematical procedures, and for the sake of convenience we are discussing up to second order correction. Now, substituting equation 5, that is the expression for wave function in 6 and in 1, then we will get h hat 0 lambda h hat dash into psi n 0 plus lambda psi n 1 plus lambda square psi n 2 etc. equal to En 0 lambda En 1 plus lambda square En 2 plus etc. multiplied by again psi n 0 plus lambda psi n 1 lambda square psi n 2 plus etc. Or on simplification, this equation changed it to the form h hat 0 minus En 0 into psi n 0 plus lambda into h hat dash psi n 0 plus h hat 0 psi n 1 minus En 1 psi n 0 minus En 0 psi n 1, that is equal to, RHS will be equal to 0. That is equation number 7, that we are performing, or we are getting that relation as a result of simple mathematical rearrangement. Since the perturbation parameter is quite arbitrary, the coefficient of each power of lambda must vanish separately. That is, the coefficient of each power, first power, second power, third power, etc. must vanish separately. Therefore, we are getting 3 important relations. We can write many more relations also, and we are discussing up to second order correction. So, we are getting these 3 important relations, and h hat 0 psi n 0 is equal to En 0 psi n 0, that is 0th order correction, and the equation number 9, that is h hat dash psi n 0 plus h hat 0 psi n 1 equal to En 1 psi n 1 plus En 0 psi n 1. And in equation 9, the power of each term will be 1. However, in equation 8, the power of each term will be 0. However, we are also getting equation 10, where we can see that the power, the total power of each term will be 2. h hat dash psi n 1, h hat plus h hat 0 psi n 2 equal to En 2 psi n 0 plus En 1 psi n 1 plus En 0 psi n 2. And for discussing first order perturbation theory, we have to begin from equation 9, where each term represents first order. And for discussing the second order perturbation, we have to begin from equation 10, since each term has power equal to 2. We ordinarily interested only the terms up to second order, and we are generally neglecting equations beyond 10. That is, we are avoiding the contribution from third order correction, fourth order correction, and higher order correction. And in perturbation theory, we are generally giving first or second order, or we are proceeding up to second order correction to wave function as well as energy. Equation 8 and 4 are identical and corresponds to zero order perturbation. Zero order perturbation means no perturbation we are providing. That means we are having the original ground state Schrodinger equation with us. That is why 8 and 4 are similar. And we have to outlook the first order correction and the second order correction. We are now discussing the first order correction to energy as well as first order correction to wave function. Later on we will moving on to the second order correction to energy as well as wave function in coming modules. Now, non-degenerate perturbation theory. The perturbation treatments of degenerate and non-degenerate energy levels are different. If some energy levels of the unperturbed system are degenerate while others are degenerate, that means for an unperturbed system some levels may be degenerate, some other levels may be non-degenerate. Here in non-degenerate perturbation theory, we shall consider the perturbation on non-degenerate levels only. That is, we are ignoring degenerate energy levels. That's why the name non-degenerate perturbation theory. Now, first order correction to energy. I already mentioned that we can move up to second order correction. And in the present module, we are focusing on first order correction. First order correction to energy and first order correction to wavelength. We have to begin from equation 9. This equation 9 is obtained from the original Schrodinger wave equation. Apply perturbation, representation of power series, rearranging the equation and simple mathematical procedures. We arrived at equation number 9. The equation number 9, each term represents the first order. So, in order to illustrate and discuss the first order correction to energy, we have to begin from equation number 9. Hamiltonian dash psi n 0 plus Hamiltonian 0 psi n 1 equal to E n 1 psi n 0 plus E n 0 psi n 1. This is the basic equation from where we are beginning the first order correction. If we wish to start the second order correction, we have to begin from the second order term, that is equation number 10, that we can discuss later. Now, we are ultimately focusing on first order correction to energy. After that, we can move on to first order correction to wave function. And to proceed first order correction to energy, first of all, we have to multiply equation 9 with the psi n 0 on left side. And we have to integrate over all the space. And we have to make some rearrangement to get a final equation. And now I will show you how to proceed the first order correction to energy. So, we have to first left to multiply each and every term that is present in equation 9 with the psi n 0 and to proceed accordingly. So, the first term is h hat dash psi n 0. So, I have to multiply with the psi n 0 from the left hand integrate. So, integral psi n 0 star. Psi n 0 star represents the complex conjugate of psi n 0. In order to get to the complex conjugate, it is a simple mathematical procedure where we are replacing the complex number I with the minus I. If there is no imaginary number, both the term psi same as psi star if there is no complex number. So, psi n 0 into h hat dash psi n 0 d tau. This will be the first term. So, I took the first term, left multiply with the psi n 0 and integrate over all space. So, the first term change into this. Similarly, on proceeding with the second term, integral psi n 0 star h hat 0 psi n 1 d tau, that is the second term changed to this. That will be equal to En1 can be taken as a constant and can be taken outside the integral sign. Therefore, the third term changes into En1 into integral psi n 0 star, we are multiplying with the psi n 0 star from left. For that, I am taking En1 outside the integral sign, and this part will be psi n 0 d tau, and the last term will be changed like this: En0 integral psi n0 star psi n0 star psi n1 psi n1 psi n1 d2 psi n1 d2. We can change this integral representation into bracket representation for convenience, and on proper rearrangement we can modify this into new equation, and the above equation can be simplified by using this bracket representation. This bracket representation implies integral, this term is simply like this: integral psi n0 star h hat dash psi n0 d2. This integral is simply represented using this bracket representation: psi n0 h hat psi n0. This is the bracket representation that is very popular in order to avoid integral, complex integral representations in quantum mechanics. We are using bracket representation. So the previously discussed equation, this equation can be changed to bracket notation like this. This is equation number 11, and this equation 11 can be further modified, and we have to apply condition for Hermitian property etc. to get to the final equations of our convenience. Since h hat 0 is a Hermitian operator, the second term on the left, that is integral psi n0 star h hat 0 psi n1 d2. This term reduces to en0 psi n integral psi n0 star psi n1 d2, and hence equation 11 can be reduced further to get En1 equal to integral psi n0 star h hat dash psi n0 d2, or using this bracket representation we can put like this: En1 is equal to this much quantity, and En1 represented by equation 12 represents the first order correction to energy. That is, the first order correction to energy En1 equal to, this term can be converted to integral if we wish, integral psi n0 star h hat dash psi n0 d2. This is the first order correction to energy. First order perturbation after the energy got after first order perturbation. This is a very, very important result. We can represent either this integral or by using the bracket representation. This is also equation number 12, and here I am using the integral notation, here I am using the bracket notation. This is the first order correction to energy. Now, moving on to further details of the first order correction. The first order correction to energy is given by simply that we learned previously: psi n0 integral psi n0 star h hat dash psi n0 d2. Here h hat dash is the perturbation. It is in a simplified form of equation 12 can be represented. It can be further again simplified. The bracket notation can be further simplified. Instead of psi n0 I can put n star, I can put n. So in bracket representation, En1 can also be represented like this. I am making a small change. Instead of psi n0 star, I put just n. Instead of psi n, here also I put n. Therefore, En1 is equal to, inside the bra, n modulus h hat dash n bra. This about the situation. En1 is simply, most simply, En1 can be represented like this. Here, the result is this result is a matrix element. This result is termed as a matrix element. Equation number 13 can be considered as a matrix element. Now, the first order correction to the energy is thus the expectation value or the average value of the perturbation Hamiltonian over the corresponding unperturbed state of the system. Unperturbed state of the system means it may be an atom or a molecule, and it is the first order correction. The first order correction to energy is an average value of the perturbation Hamiltonian corresponds to unperturbed state of the system. We previously known about average value postulate. We can find out average value using Hamiltonian operator. Energy average can be calculated by using Hamiltonian operator. In a similar way, we are getting the first order correction can be considered as an expectation value or average value of the perturbation Hamiltonian over corresponding unperturbed state of the system. Thus, we get the energy corrected to first order as En equal to En0 plus m lambda h hat dash n. We can put m instead of n, we can put m. M is some other function, n is other function. We can use the general form like this. N is equal to En0 plus this integral value, and we are getting this energy equation in final, where En0 is the ground state energy of the system, En is the corrected energy, and this last part represents the first order correction. So, the total energy of the system after first order correction will be equal to the ground state energy plus energy obtained after first order correction, that is represented like this. The first order correction to wave function is our next step. So, energy and wave function are two important parameters, out of which we are performed the first order correction to energy. Now, we have to give first order correction to the wave function. So, in order to give the first order correction to the wave function, first of all, we have to fix the wave function. In first order correction, the wave function is written as a linear combination of unperturbed eigenfunctions of the system. This point is very, very important. We need a wave function, and that wave function must be a linear combination. Linear combination of what? Linear combination of unperturbed wave function, unperturbed wave functions or unperturbed eigenfunctions of the system. Mathematically, we can represent psi n1, wave function for first order correction, equal to summation of I is equal to 1 to infinity ai psi I rise to 0, ai psi rise to 0, or simply I begins from 1 to I may have values up to infinity. We already have the starting expression, equation 9, and based on that we are performing first order correction to energy as well as wave function. We already have the mathematical expression lambda h hat dash into psi n0 plus h hat 0 psi n1 equal to En1 psi n0 plus En0 psi n1. This is very popular equation number 9. This we obtained by starting from the very simple Schrodinger wave equation, and this based on this equation we are proceeding further and moving on to first order correction to the wave function. Now, psi n1 is a linear combination, that is represented by equation number 14, and we already have equation number 9 with us, and we have to substitute the value of 14 instead of psi n1. That is, in this expression there is values for psi n1. Psi n1 can be replaced by this value, and here also there is psi n1. Psi n1 can also be replaced. That means we have to substitute this equation 14 in equation 9 and proceed accordingly, that we done in the case of the first order correction to energy, where we have to left to multiply with the psi m0 star, and we have to integrate over space. And if we are proceeding, we will get like this. The first function we have to left to multiply with the psi m0 star and integrate. So, this term changed it to integral psi m0 star h hat dash psi n0 d tau plus the second term can be corrected, and we can put psi n1 is equal to this quantity. So, the expression will be integral psi m0 star h hat 0 into sigma I is equal to 1 to I is equal to infinity, AI psi I or AL psi L. I or L can be conveniently used for representing the variable functions. D tau, that is equal to, energy can be taken outside the integral sign. So, En non-integral, left multiply with the psi m 0 star psi n 0 d tau plus the last term would be En 0 can be taken outside the integral sign into psi m 0 star, psi n non can be replaced by this integral I is equal to 1 to infinity AL psi L 0, and we are getting this expression. This lengthy expression can be further simplified, and finally using Bra and Ket representation. After the Bra and Ket representation and final simplification by applying the condition for Hermitian property, we get the expression AM, where AM is arbitrary constant that depends on M. AM equal to psi m 0 h hat psi m 0 divided by En 0 minus Em 0, or this integral can be further simplified like this. This term is integral psi m 0 h hat dash psi n d tau divided by En 0 Em 0, or the final equation Am in integral form can be represented like this integral. This M is nothing but psi m 0 star h hat dash psi n 0 d tau, psi n 0 d tau divided by this term, that is En 0 minus Em 0. So, this about Am. Evaluating the coefficient An and Am and apply the condition for normalization, we get the final expression for first order correction to energy. The first order correction to energy is like this: sigma m, this integral part, bra m modulus of h hat dash n closed divided by n 0 minus em 0 into psi m 0 d tau. This about the first order correction to energy. This all these are complicated integrals, and we can represent it in the simple form like equation 16. Consequently, the wave function corrected to first order can be represented like this. That is, psi n 0 is the wave function, the ground state wave function of the system. Psi n is the perturbed wave function, and this term represents the first order correction. So, to get the corrected wave function, we have to add first order correction to the ground state wave function. So, this is the wave function of the present system under consideration. The wave function of the system is equal to ground state wave function of the unperturbed problem plus first order correction to wave function, and this second term represents the first order correction to wave function, or simply we can put like this: psi n is equal to psi n 0 plus psi n first. This is first order correction. This is ground state or unperturbed wave function. So, the wave function after first order correction, wave function of the quantum mechanical system after first order correction is psi n equal to psi n 0, unperturbed wave function psi n 0 plus first order correction to the wave function. So, this about the expression, and here psi n 0, psi n 1 is replaced by this parameter. So, we are getting the final expression after first order correction. This is the wave function of the system after first order correction to the wave function, and here there is a prime in the summation, and the necessity of that prime is indicating that the summation, we have to avoid one term from the summation. That means m is equal to n should be excluded. We have to exclude the summation term when m appears to be equal to n. Thus, we have discussed the first order perturbation theory. On conclusion, we have to say some important points also. Perturbation theory express the solution to one quantum mechanical problem in terms of other problem. That means we must have a reference problem which is already previously solved. Based on that, we have to find a solution to an unperturbed problem. So, perturbation theory express solution to one quantum mechanical problem in terms of other which is already solved exactly. So, we can make a first order, second order, higher order corrections either to energy or to wave function. And in this module, we focused on first order correction to energy and first order correction to wave function. That all about the present discussion. Have a nice learning experience. Thank you.